Here we have an oil having a specific gravity of 0.9 that's pumped in with a water jet pump. You can see the oil is coming up here from the bottom. The water volume flow rate is given as 1 meter cubed per second, and the water and oil mixture has an average specific gravity of 0.95. We want to calculate the rate in meters cubed per second at which the pump moves the oil. So essentially what we want to do is find Q2. So that's Q, the volume flow rate, down here that's coming up. That's what we're looking for. Alright. First of all, let's look at our equation we've got that we need. We have two inflows. We've got the water and then we've got the oil. They're going to come in and then they combine and then flow out of section 3. So we could write that M1 dot plus M2 dot has to equal M3 dot. Right? Now we can rewrite that in terms of Q, and we could say that that is rho of the water times Q1. Remember, Q is V times A, so velocity times area. And so rho W times Q1, that takes care of M1 dot. M2 dot, that is going to be rho of the oil times Q2. Q2 is what we're looking for. And then that could be equal to the density of the mixed fluid times Q3. Alright, so if you knew to use this equation, you could use that one, or you could use the long conservation of mass equation with the integrals, and we'll go through that now and show you that you get the same thing. So if you remember, for conservation of mass, we have the partial with respect to t of the integral of the control volume times rho d volume plus the integral of the control surface of rho times the velocity vector dotted with n times dA. Now we don't have anything changing with time, so let's just get rid of that. That goes to 0. Also, this whole thing needs to equal 0. Forgot about that. Okay, so now let's go through and find this. Remember, for this type of application, when we use this equation, we need to find the velocity vector and n for all of the inflows and outflows. So if you go over here and come up with your control volume, I'm just going to put little dashes here. We got that. We're going to have an inflow here. Right, so this will be V1. Now remember, n goes out from the surface of the control volume, so that'll be going to the left for N1. Now we're going to have a V2, and now n is going to come down because, again, we want to go out. And then our volume here for V3 will go to the right, and then N3 will go to the right also. Okay? So keep that in mind as we write this out. So now let's look at the water, which is at section 1 first. So if we look at this portion of the equation, we need rho times V dot N times dA, essentially. Alright, so we're going to have rho of the water. Then we have the V dotted with the N, so we're going to have V1I dotted with a negative I. And then we're going to multiply that by just A1, whatever that is. We weren't given that. Now let's go to the other section. Let's do section 2 next. So here we're going to have density of the oil times V2, so that'll be V2J, dotted with N2. N2 is going to be negative J, and then let's just multiply that by A2. And then finally for section 3, we're going to have the density of the mixed fluid times V3, so V3 will be V3I, and then we're going to dot that with N3, which is just I, and then multiply that by A3. Now that whole thing needs to equal 0. So if you go through and multiply all this, do the dot products and everything, you're going to end up with negative rho for the water times V1A1 minus rho of the oil times V2A2, and then plus rho for the mixed fluid times V3A3, and that needs to equal 0. And if you remember that Q is the velocity times area, you'll notice that you get exactly what we had up here. Okay, so we could rewrite this then and say that this is rho of the water times Q1 plus rho of the oil times Q2. Let's move this term over to the right, get rid of our negative signs. So that'll equal rho of the mixed fluid times Q3. So notice that this equation here is the same thing we had up here. Okay, this just went through and showed you how to get it. Now let's plug in our values that we have. We know what row of water is, the density of water that's easily found in a table. That's 998. Our Q1 was given to us, that was 1. Row of the oil, we're not given the density, but we are given the specific gravity, which is 0.9. And remember, we can relate specific gravity and say that that is row of the oil over row of H2O. So in this case, for the density of the oil, we can write that that's 0.9 times 998 times Q2. And then again, for the mix, we were given the specific gravity, that was 0.9, so for the density of the mixed fluid, we'll have 0.95 times the density of the water, which is 998 times Q3. You can see that these 998s are all going to cancel. That leaves us with 1 plus 0.9 Q2 equals 0.95 Q3. Now remember, what we want is this Q2. We still have this Q3 in here, so we need another equation so that we can solve, because we can't solve for two unknowns right now. So the other thing we need to recognize is this is going to be incompressible. So we're going to have an incompressible flow here. So with that, we can say that the summation of the Q's for the out are going to equal the summation of the Q's for the inflows. So that's going to give us that Q1 plus Q2 equals Q3. Right? I've kind of written those backwards from what I have up here, but Q3 is our outflow, and then these 1 and 2, those are our inflow. So with this, we can get an equation for Q3. We know that Q3 has to be 1 plus Q2. And with that, we could take this equation here, plug it in right here. And then that'll give us one equation with one unknown, where Q2 would be the unknown. So if we do that, we get 1 plus 0.9 Q2 equals 0.95 times 1 plus Q2. So Q2 here equals 1 cubic meter per second. Alright, so that's the flow rate of the oil, section 2. So again, we get 1 meter cubed per second.